So I'm ready whenever you are.
Okay, so I think we can make a beginning, shall we?
Sure.
So, Amit, can you introduce the chairperson, please?
Yeah. So, hello everyone. Welcome back to this session. This session will be chaired by Professor Ameeya Bhagwat, who is an associate professor at CEBS and is interested in theoretical nuclear physics. He did his PhD from IIT Bombay and was then a postdoc position in France and Sweden, and then was a faculty member at IIT Gandhinagar before joining CBS. I would now request Professor Ameeya Bhagwat to chair the session. Thank you.
Thank you, Amit. Nice to hear from you after a long time. So let's make a quick beginning. Okay, so welcome to the 10th session of this symposium. We have 4 talks in this session, and the theme generally is the physics of fluids. We have 4 talks, as I said. There are 3 invited lectures, the first by Professor Rahul Pandit, the second by Professor Sudhir Jain, the third by Professor Bhooshan Paradkar, and the fourth is by our own student, a former student, Aklant Bhowmick. So let's invite the first speaker. Professor Rahul Pandit, he did his PhD from University of Illinois at Urbana-Champaign. Currently, he is a professor at IISc Bangalore, a noted expert in the areas like turbulence and spiral and scroll wave turbulence and all those things. Recipient of several prestigious awards, including Shanti Swarup Bhatnagar Prize. It's a privilege to have you here, sir. So over to you, Professor Pandit.
Thank you very much for your kind introduction. I will talk today. First of all, I want to thank all the organizers for giving me this opportunity to speak at this symposium. I will say a few words about Professor Chitre later on. I will talk about Cahn-Hilliard-Navier-Stokes turbulence, which you probably will not know about, so I will give you an introduction as we go along. This work would have been impossible without several people, in particular Nadia Bihari Pradhan, who is probably in the audience. He has done a lot of the work that we talk about today. Also Prasad Pedlekar, John Gibbon, Norita Pal, Anupam Gupta, all of them except John, of course, are my students. And I would like to acknowledge support from CSIR, DST, UGC, and SERC, which is our supercomputing center. I would like to dedicate this talk to the memory of Professor Chitre. Unlike many of you, I did not have the good fortune of working with him. I only knew him from a distance, and also he was a very good friend of my uncle, who was also a professor at TIFR, Lalit Pandit. And so the families know each other very well. So it's a great honor to be able to talk in his memory. We have published several papers on this subject. I will not bore you with details. Let me begin in a simple way with an outline, an introduction, then model equations for binary and ternary fluids, results from simulations, if we have time, some mathematical digression on the regularity criteria for solutions of these equations, and then conclusions. So why are we interested in this system? Well, in nature, there are many binary fluid flows. I show you on the left clouds, and on the right a schematic diagram showing droplets inside a cloud. So it is by its very nature a multi-phase flow. Even a warm cloud which has no ice has got 2 phases at least. And then, of course, there are droplets of oil in water, like here, or bubbles in a turbulent flow. I have given all references down here. Perhaps you can't see them, but those of you who are interested, I can tell you more as we go along. And here is the beautiful object called an anti-bubble, the photograph sent to me by my former student, Chirag Kalelkar, who is in IIT Kharagpur. This is a sort of I'll describe it as I go along. It's a shell of a low-density fluid inside a high-density fluid. It's a wonderful object. Then there are ternary fluid flows, for example, a compound droplet, which has been used, it has been suggested as a way of doing an analog simulation of a white blood cell here. And then here in the middle, there is a bubble passing through a liquid-liquid interface. And then there is the so-called Faraday instability shown here on a floating droplet. So let's try to begin. First of all, suppose we were not worrying about the fluid part, but we were worrying about two phases, A and B, a homogeneous mixture separated by an interface. This happens all the time in statistical mechanical systems. If you are below the consolute point, the two phases coexist, but if you start them all off together, then they phase separate. And I'm showing you here an illustrative plot. We are going to distinguish between the two phases by what a theorist would call a scalar order parameter phi. So these are contours of phi. And you can see that as time goes along, the red phase separates from the blue phase, right? That's phase separation without any fluid. This could apply even for a magnet, an upspin phase and a downspin phase. All right. So how, suppose I were teaching a course on statistical mechanics and I asked, how would you describe a system in which there is this sort of phase separation? And the standard way of doing it is introducing a Landau-Ginzburg free energy functional, which has a potential here, V of phi. Typically, it's taken to be a double well. So here is the double well, 1 minus phi squared whole squared. So it has minima at plus or minus 1. One minimum is associated with one of the phases, let's say A, which was, say, red in the old plot, and the other is minus 1, which is blue, say B. And then here is a term, grad phi whole squared, which is the free energy cost for having an interface, because grad phi is large wherever you go from one phase to the other. And so that will give you the free energy cost for having an interface. And phi will change continuously as you go from A to B. So this is a problem that we often give in our advanced statistical physics course. So for example, let us say we have a diffuse interface because it's not exactly sharp. Then if you say that the interfacial profile, the order parameter phi varies only along one dimension, which I call y, then a functional derivative of that free energy functional set equal to 0 to minimize will lead you to an ordinary differential equation, and subject to these boundary conditions that at one end you have one phase and at the other end you have the other phase. And in this particular case, you can actually solve it analytically and it gives you the smooth interfacial profile, right? But of course, when you have two fluid phases, life is more complicated. So, you know, the fluid must come in some way. And the simplest set of equations, which describes the motion of such two-phase systems, which are both fluid, is called the Cahn-Hilliard-Navier-Stokes set of equations. So all of you have probably seen Navier-Stokes. So if U is the fluid velocity, up until here is Navier-Stokes. This is the viscosity term, that's the advection term, here's the pressure. And then there are some extra terms here having to do with the interaction between this order parameter and the velocity, okay? Divergence U is 0 because we are at low Mach numbers in most of these cases. So we assume that the fluid is incompressible. So that, if you like, is the momentum equation along with the stress from the scalar field. And in turn, here's the equation for the Cahn-Hilliard order parameter phi, but now it is also advected by the velocity field. And if you've never seen these equations, of course, you will not learn about them completely from this talk, but suffice it to say that there is a well-defined set of equations by which we can begin to follow not only the scalar field phi, which distinguishes between these two components of the binary fluid, but also the velocity fields that are generated as we go along. All right. There are many parameters, which let me not go through in complete detail. There's a mobility, there's a friction if required, there's a chemical potential here, which is related to a functional derivative of the free energy that I mentioned, and so on. And two important parameters. One is the width of the interface between the two phases, which is what we would have got here if we had sorted this out in complete detail. That would give you a width of the interface. And then the surface tension, because the moment you have two coexisting phases, there is a surface tension between them. All right. There are many important advantages of such diffuse interface methods in studying binary fluid flows, because you don't have to specify anymore, which you would have to do if you had a completely sharp interface, boundary conditions on a boundary that changes in space and time. Okay, so if you have enough patience and you are a good driven graduate student like my student Nadia, you can actually even do this for 3 components, where you have to keep track of 3 concentrations, C1, C2, C3, and then there's a free energy, and I will not worry you with details. And you have to represent it in a Gibbs triangle, etc. The vertices of these triangles are the the pure phases. The edges tell you how you go from one pure phase to another, and so on. And then you can write down the Cahn-Hilliard-Navier-Stokes equations for the 3-phase case. Now, so some of this talk is to be built on faith. You have to have faith in me that I've given the right equations. Of course, I have not explained every term in them. For those of you who study turbulence will know that there are control parameters which are dimensionless, and the Reynolds number, well known to everyone, is certainly an important control parameter. But by the time you're looking at these binary fluid flows, there are many other dimensionless control parameters. For example, there's the bond number or the Weber number, both of which are related inversely to the surface tension, and the capillary number, the Cahn number, is a dimensionless measure of the thickness of the interface and so on. Now, given such equations, of course, all of you must know that even with the Navier-Stokes equations, we can rarely get any information about the turbulence in that system by using fully analytical means, so we have to go to a computer. And even with these equations, which are even more difficult, we have to go to the computer, and we use typically pseudospectral methods, and my students have developed their own codes, which they run using all sorts of software, including software which makes it possible to run them on graphics processing units using CUDA and so on, or massively parallel pseudospectral, Fortran and C codes. So given all this, let me give you a sort of illustrated guide through different phenomena that we can study in the turbulence of binary and ternary fluid flows by using the Cahn-Hilliard system. Most of the time I'll do 2 dimensions, but not always. So let us first look at how a droplet moves when the whole fluid is stirred in some way called Kolmogorov forcing. So let's see, there's a little minority phase droplet in blue, in a background of a majority phase red. And there we go. You can see how the droplet distorts and moves around. And you can study it in as much detail as you would like. Now, of course, it's always nice to have movies for talks, but if you're a physicist, you have to actually get some quantitative data out of it. So I'm not sure you can see this slide very well because, let's see, let me blow it up a bit just to illustrate. So in this left-hand slide, I've shown you a sort of dimensionless measure of the perimeter of this droplet. And you can see that especially if the surface tension is very low, the system looks like very intermittent spikes and so on. And we all know that in turbulence, such intermittency leads to multifractality. And in fact, my student Norita Pal did analyze this using multifractal techniques and did show that indeed there is a multifractal spectrum, and the smaller the surface tension, the more the multifractality. Often in turbulence, we characterize the turbulence by an energy spectrum. At least some of you must have heard about the Kolmogorov energy spectrum. You plotted E of k versus k, and this purple curve is what happens when you have a single fluid, and that gives you a minus 5/3 spectrum. If you don't worry about too much subtlety. The moment we add the second component, the binary fluid, this part of the spectrum gets pushed up. And this is an effect that is akin to what is seen in turbulence with polymer additives, a problem that we have also studied and is related to dissipation reduction. But again, I will not go into such details here. All I wanted to show is that given this Cahn-Hilliard-Navier-Stokes system and our ability to simulate it on a computer, not only can we study it qualitatively via nice movies and so on, we can actually quantify what effects it has on various measurable statistical properties like the energy spectrum and so on, all of which I will not cover in detail. Let me cover one more thing that happens. I had at the beginning of this talk shown you how the red and the blue phases separate from each other. Here that's shown in black and white. But now suppose you make this turbulent, it turns out that the turbulence can arrest this phase separation, because the surface tension would like these two phases to separate, but the turbulence wants to scramble them up. And indeed, you can characterize this coarsening arrest, as it is called, which is what I did several years ago, along with a former student of mine, Prasad Pedlikar, who's now at TIFR Hyderabad, and Norita Pal, who's now at Los Alamos. Now, what you can do with one droplet, you can study with many droplets. There is a huge variety of behaviors depending on this many control parameters that I mentioned. Here you can see that the droplets are all sort of coalescing, and eventually only a few will be left. So characterizing the statistical properties of such turbulence is a challenge, partly because you have to keep track of a large number of control parameters. But I will not dwell on that any longer now. Now let's look at some ternary fluid flows. Let's look at coalescence of droplets and lenses. So, for example, if I blow it up a little bit, you can have a lens here of two lenses of blue phase between two other phases, green and brown. And let's start, and you can see they coalesce, and you can see in this corner here the red line going up, showing how the height of that bridge in the lenses is going up in time. And okay, so again, you can make nice movies, but you can actually get quantitative and make a sort of log plot of the time dependence of the scaled height versus time. And even though superficially it might look like the flow is not turbulent, there can be both regimes, and these are data from simulations that Nadia has done. And there are two different regimes. This h of t goes as the first power of t in the viscous regime, and where the inertial effects are important, it goes as t to the 2/3. This has been seen in experiments, but as far as I know, this is the first time it has been seen theoretically in simulations. So this is work that we are about to write up. All right, I mean, there's more on lens coalescence and so on. Let me not go there just now. All right, so anti-bubble, which we have just put on the archive. So I told you what the anti-bubble was. Now it's a phase which is less dense inside this thing. So let's see how it evolves. This is how the phase field is evolving, and this is how the vorticity is evolving. And you see, finally, it becomes one bubble. And this is completely consistent with measurements, which has never been seen before in simulations. And we have, well, we've submitted for publication this paper, which at least I'm very fond of. So you can do droplet coalescence. Let me show you some nice movies. The movie on the left is the phi field. The movie on the right is the vorticity field. That's, you start with a toroidal configuration, and this is what it does. And we can follow it in complete detail in the full spatio-temporal evolution using the Cahn-Hilliard-Navier-Stokes equations. Let me show you a few more nice movies before. So I told you about bubble entrainment, a bubble going through an interface between two fluids. So let's see how it looks like here. So this is also done by Nadia. So here's the bubble going through, and on the right-hand side, you see the vorticity, how that evolves. And you can see the train of little mini bubbles that break off and then go back down. All right, so all this requires that you have the ability to use these equations on a computer and so on. So last, let me quickly tell you one thing. We all write down these equations of hydrodynamics like Navier-Stokes and Euler, and now I'm telling you about Cahn-Hilliard-Navier-Stokes. I mean, what sense does it make? You know, typically physicists don't worry about it. I know when I teach even existence and uniqueness of solutions for ordinary differential equations, a typical physics student will tolerate it because someone is saying it, but thinks it's just a matter of detail. But it's actually a matter of great detail, because in 3 dimensions, the Euler equations, which is Navier-Stokes with 0 viscosity, it is 265 years old, but we still do not know whether with arbitrary initial data, which are analytic, do the solutions develop a singularity in finite time, or do they not? And there's a long history. In fact, if you can answer that question from Navier-Stokes, you get $1 million from the Clay Math Prize. So there is a so-called Beal-Kato-Maida theorem for the 3D Euler case, which basically says that you don't have to look at every quantity that comes out of an Euler simulation, but you just look at the maximal value of the vorticity, and you integrate it up to some time t star, and so long as this is less than infinity, then there is no singularity. But at the time t star at which it is infinity, then there is a singularity. But that's all that we. It's only a criterion. It's not a proof. Okay, so we could do the analog of this for the Cahn-Hilliard-Navier-Stokes case, and this is with John Gibbon, who's a real mathematician, and the analog of omega infinity is E infinity, which is the sort of basically the energy part in the free energy functional plus the part which comes from the fluid. And so that just to give you just a quick overview of what we can learn from the Cahn-Hilliard-Navier-Stokes system. And then while you ask questions, I can play you my last movie, which is a movie of the Rayleigh-Taylor instability carried out by using our Cahn-Hilliard system. Thank you very much for your attention. Hello, any questions?
Thank you very much, Professor Pandit.
So
if there are any questions, anybody wishes to ask a question, may raise your hand, please, and we will take the question. If not, let's thank the speaker again for a beautiful talk, a very exciting talk. And thank you very much for this wonderful presentation.
Thank you for having me here. I'll stop sharing my screen now.
Sure.
I think someone was trying to say something.
Oh, is it? Who?
Is there a question?
Not that I know of. Oh, yes, there is one. Sorry, there is one question. We missed it. All right. So the question is the following. Would the fluid drop break apart due to a high amount of forcing? How can this be understood intuitively as it has to overcome the surface tension? It's a question from John Sunil.
Yes, of course. The answer is yes. It can get torn apart. And so the lower the surface tension, the easier it is to tear it apart. So if you have a low surface tension, you can do it at low Reynolds number. But if you have a high surface tension, then you need to go to higher Reynolds number to tear it apart. That's all. It's exactly what physics would tell you. You can try it with a mixture of oil and water, even in the buckets.
John has one more question. He's asking, could you qualitatively explain the difference between instability in the normal NS and the CHNS?
Well, I mean, how shall I say? You have to specify which instability. I mean, there are hundreds of instabilities. For example, there is the Rayleigh-Taylor instability, which I showed at the end, which is a heavy fluid sitting on top of a light fluid. And then you put any minor perturbation on it, you can see that it will grow. And that's how eventually the heavy fluid will come down. And when you have the Cahn-Hilliard-Navier-Stokes case, there is, of course, you account for the surface tension, and therefore you can keep track of the interface without having to handle boundary conditions on a moving interface, which is how we did it. So some things will be related, some things will be new, but you have to specify which instability and then go from there.
So I was asking about the Rayleigh-Taylor instability. Like, is there some kind of feature which is seen in the Cahn-Hilliard system which is not seen while solving the normal Navier-Stokes?
I don't think so. I mean, there are people who have long debates about it. I mean, there are people who like Cahn-Hilliard-Navier-Stokes and people who don't. So the people who don't like Cahn-Hilliard-Navier-Stokes say, okay, you don't have to keep track of a moving boundary, but if you look at the sorts of interfacial weights that you can get in your direct numerical simulations, they are not as thin as they are in experiments. Well, but then it gets into a level of detail, but I think, at least in my heart of hearts, I don't believe there'll be anything wrong with what we do with relaytelling.
Thank you.
Any further questions, John, or anybody else who wishes to ask a question? If not, then we thank the speaker again. Thank you, Professor Pandit, for this.
Thank you very much. Thank you.
All right, so we move to the second talk of the day, of the session, and it is by Professor Sudhir Jain. He has a very long association with CBS, more than, he has been associated since 2010 or even before that. He is currently a scientific officer at BARC in the nuclear physics division, and he's an expert in theoretical nuclear physics, then semi-classical nuclear physics, nonlinear dynamics, and so on. And right at present, he is spearheading the DAE activity, particularly the BARC activity on quantum computing. I can talk a lot about him. He's an old friend, but I won't spend too much time on that. So may I invite now Dr. Sudhir Jain to present his talk.
He was here right now, just now.
Yeah. I don't know where is he.
He probably got disconnected.
Could be, yes, because
you were seeing him just now.
Yeah, was very much around. Ah, there is he.
Disconnected.
Professor Sudhir, can you try saying something? We can see your video, but we can't hear you.
Start the video, please. Pratyush, can you figure out what's happened?
Yeah, we can't. First off, we can't hear you. We do see what you're presenting. We see your.
If he navigates to his presentation, then we will be able to see his presentation.
Ah, okay. So he has to go to his PowerPoint presentation. I think he has shared his screen.
Yeah, he has shared his screen, but he will have to unmute or maybe join because we can't hear him at all.
Yes.
Can you try pressing the arrow button in the bottom left corner right next to the mute button? Yeah, it is connected, but we are not able to hear you.
Maybe the browser doesn't have microphone permissions.
Are you able to hear?
Yes, we hear you.
Yes.
Okay. And now is the screen shared?
Yes, it is.
Okay. So, so can you see the screen and can you hear now?
Yes, both.
Yeah, okay. So I will begin this talk now. With your permission, Ameeya, should I begin?
Absolutely.
Okay, so I'm going to talk about something that I did quite some time ago, and it's a case of Kelvin-Lakes in a charged fluid. It's a very simple exercise, unlike very complicated and involved talks, and so I think it's best that the students listen to me and the experienced people can go and take a walk or have a cup of tea. It's enormous honor for me to be presenting this talk. It's dedicated to the memory of Professor S.M. Chitre, who I who I had known for 37 years. And this is a picture just on the day when the first permanent appointments were made at CBS. And he has the envelope which contains the grades given to all the people who appeared for interviews and so on. So very, very close and long association, not only scientifically but also personally and so on. So yeah, I mean, very personally, I miss him almost every day. So okay. So what we are going to talk about is something which is a spectacular sight and I think of great interest. When we go around, we look at these wakes, and as you see in this picture, there is a certain universal aspect associated with these wakes, and this is a textbook matter. All the textbooks on water waves, particularly for students, a great book on waves in fluids by Sir James Lighthill contains a beautiful chapter on water waves and actually the entire waves in fluids. So it's a very beautiful subject in mathematical physics, and the wakes behind these objects which are moving on a calm water, as one can see clearly, you may have a ship or a duck or other things. And these are of course very beautiful and very nice to look at. So that's the poetic aspect, and the scientific aspect and the mathematical aspect is in trying to explain this. And explanation was done long ago by Lord Kelvin. But before I go to that, I'm going to summarize that very textbook type of matter. That's why I would apologize to experienced fluid mechanics experts to pardon me, to be spending time with my students who are very dear to me. And so there are other practical implications which are of importance. One is connected to the drag force on ships. As the ships move and there are wakes, these wakes are in some sense like Cherenkov emission. And they carry the energy emitted by the waves going at that angle, which makes a cone. This is a Mach cone actually. This is of importance to drag force on ships, and therefore it's of importance in naval hydrodynamics. So there's a lot of very practical type of application. I will touch upon it towards the end of this talk, and there are reasons more than just the beauty and the mathematics for which I was interested in this problem. The other thing is that in research carried out by the departments of coastal, port, and oceanic engineering, there is this problem of bank erosion on navigable waterways. And this also is connected to this question which we are trying to understand. Let me therefore start very simply. This is it's taken from the James Lighthill book, which I was recommended to study by Professor Chitre back in 1984. Just as the equivalent condition for acoustic emissions from supersonic aircraft from consideration of stationary phase, the phase of signals emitted by the ship at successive instants is stationary at a point P of observation if the component of ship's velocity in the direction of the point where you're making observation equals the wave speed. So that's a phase speed. So this summarizes the whole philosophy of doing this calculation using stationary phase condition and the resonance condition, which is coming from the Cherenkov radiation. Now, let me straight away get into the phase speed of the surface gravity waves. And this is as a function of wavelength. It satisfies the omega k relation. The dispersion relation is omega equal to square root gk. G is 9.8 meters per second square approximately on the surface per omega equal to square root of gk. And therefore, very simply from what we know in school, or early college, is that the phase speed is then omega over k, which is then square root of g by k, and the group speed is a derivative of omega with respect to k, and that turns out to be half of the phase speed for these waves. If we look at the wave packet, so propagating with this group velocity with this wave number k, it covers a distance in a certain time t, which is r equal to vgt, and I can put this expression and just invert it around, so k is gt squared by 4r squared. I would like to add that what I'm going to, the level of discussion that I'm going to keep at is very elementary, and there is no sophisticated mathematics at all that I'm going to get into at all. I just indicate that there are certain complicated things which need to be done in a very technical way, but I'm not going to present any of them. Now, using this k, we can actually find phase, because phase is basically omega t minus k dot r, and therefore k can be written as a minus the partial derivative of phase with respect to r, which allows me to write phase as an integral of minus k dot dr. If I take this 1 over r square and I do an integral over r with a minus sign, I get gt squared by 4. This presentation, which is on the basis of wave packet propagation, has its own limitations. But okay, again, we will not talk about it. Let's just enjoy what we can see, how well we might still in this simple analysis be able to get to understand what we observe in nature, which we are very interested in. As the ship moves at a speed faster than the phase speed, the waves emitted is simply an instance of Cherenkov radiation. So here we are talking about Cherenkov emission in dispersive medium. And what happens is that this is, I think the X and Z are opposite. This is a typo. So there is a localized source, and this localized source produces a series of small local perturbation, and each of these local perturbation, because of the symmetry that we consider, that there is a calm water, generates a lot of circular waves. And if we consider two of these at times t and t plus delta t, their radii differ by the phase speed times the delta t, because this is the circular waves are the same phase. And so this is the difference in the radii of the wavefronts. And the distance it has traveled is v0t, and therefore in the time delta t, the distance traveled is v0. v0 is the speed of the object, which is moving, creating waves behind. And so the waves are emitted at an angle theta, and this theta is given by the cosine of theta, which is the ratio of the phase speed to the speed of the object. And so a Cherenkov emission takes place if the z component, which is this horizontal component, so x and z are here interchangeable, as I said, the omega 0 times kz is equal to the frequency. And this frequency is also omega p times k, where omega vp times k is the phase speed. V0 is the speed of the object. When this happens, is a resonance condition satisfied. And so that gives us a condition on the speed of the object, which is moving in water like a duck or a ship. If that speed is phase speed times k over kz, then there is going to be an emission of waves in a certain way, which we have to still understand what that is, which is what Lord Kelvin explained to us. We are trying to therefore understand how do the wave packets propagate with their group velocity. So the distance from the source to the point of observation is, as I said, the group velocity times t, because it's a dispersive medium. This is not equal to the phase speed times t. They will be equal if it's a non-dispersive medium. And this is because the group speed is half of the phase speed. We can write half VPT, and then we have this condition coming from this cos theta VP by V0, and this then immediately this very simple analysis gives us the possibility of calculating coordinates of the observation point in the frame of reference, moving bodies at the center. Moving bodies, so this is the center, this is our frame, and in terms of that, we can actually write down x and z, the coordinates of the point. So this point here is r cos theta, r sin theta, and we want to write, and this is on the constant phase circle. These points are on constant phase circle, and we would like to actually find out the pattern of the waves created by putting all the waves together for all constant phase surfaces. That's what we see as a pattern. And so this can be simple geometry. X is r sine theta and z is v0 t minus r cos theta. These are read off from here, r sine theta and r cos theta, and then there is this speed v0 t. So just by that, we have simple expressions involving no complication at all. And now we can eliminate r and t both in favor of phase, since we actually want to study constant phase. So we eliminate r and t in favor of phase, and we can do that because we have these relations. We can do that. This gives us the coordinates of the observation point, and the emission of waves have a pattern which are inside a certain angle 2 alpha. This is the cone that we observe in the picture that I've shown you. And this can be found by putting the condition of dx by d theta equal to 0, because we want to say stationary phase. And if we do that, we find that theta naught turns out to be tan inverse of root 2 by 2. And if I calculate tan alpha, which is x over z, for this value of theta naught, which gives me the Mach cone, the cone angle, the total angle. This is by substituting the value of theta naught in these expressions, we get square root 2 by 4, and the inverse tan of that gives us 19.5 degrees, actually 19.479, so on degrees. And the twice of that is the 39 degrees, which is the angle that we observe behind the ship. That explains that why this is this angle, and there is no dependence here on the speed. The speed of the object actually cancels in the calculation because of the v0 square and the v0 square here in the constant phase, and therefore it does not play a role, and therefore it's constant. And this was explained by Lord Kelvin a long time ago. So yeah, I thought we just present that to revise. This is how it looks. This is a wave pattern which looks like that. This is the object which is moving in this direction. And these patterns can be immediately obtained by plotting x and z with spatial coordinates. This is not a problem. Now I want to come to charge fluids and want to come to ion acoustic waves. Why particularly ion acoustic waves? There's one reason which will come towards the end. That's a very complicated reason, so I want to avoid that. The simple reason is, rather a simpler reason, is that some of the equations satisfied by water waves, particularly shallow water waves, are very similar to ion acoustic waves. The mathematical structure of the equations are very close to each other. So while I was teaching a course in nonlinear plasma theory, and with some applications to certain of our problems, I realized that actually uh, one can actually develop a lot of analogous solutions for ion acoustic waves, linear and nonlinear. And today, of course, here I'm talking about linear ion acoustic waves. Ion acoustic waves for younger folks who are in the audience are um, simply sound waves in plasma, which are because of the small oscillations of ions. And ions are much heavier than electrons, therefore the ionic temperature is taken as nearly as zero. There is temperature only of electron, and one can write down simplified equations. They are still somewhat nonlinear, but when we linearize that, and once we linearize that, one can actually derive dispersion relations and show existence of ion acoustic or ion sound waves. Dispersion relation in this case is is omega equal to CSK by 1 plus K squared D square root of that. And this CS is the speed of sound here, and D is the related to characteristic length in plasma. So that is all the charge and everything connected to it. Yes. Yeah. So the electron temperature divided by like 4 pi e squared, the equilibrium density. So that is D. It's a length scale characteristic in plasma. So this is dimensionless, and omega equal to CSK over this. So this is again a dispersive system. It's a dispersion relation, and one can again write down the phase velocity and the phase speed and the group speed. And so we see that short wavelengths propagate slower than longer ones. You can see here. So now, if we again consider a local pulse source, so we are saying that something is moving in the plasma, and we are trying to study what is the nature of waves which are being emitted. We do the same analysis as I've shown earlier, which Lord Kelvin did. We do the same thing, except that we are slightly different system, and the group speed is R over T. Speed is this, and of course, if your pulse source, it moves and travels a distance r in time t, which is r equal to vgt. So using these, we can actually express k in terms of 1 over d times this expression. This is basically very simple manipulation by putting these two things together. And we can then calculate the phase in the same way. And the phase has a fall like that with distance. The source not strongly local, the wave packet is localized near this point. So here you can see some undulations which will damp to zero if it's not a very well localized wave packet. The source is also big. So ion acoustic wave dispersion is weak and dominated by K times D, where D is the length scale. So weak dispersion is much easier. So Cherenkov emission is much easier to explain. Dispersion leads basically to slight broadening of the wave packet near the Mach 9. The generation of slower wave component looks exactly the same as the temporal emission as seen here in this graph. So now in the general case, where we are not talking about, we are not restricting to weak dispersion, we again use these two expressions, and we are basically wanting to get to the coordinates of the point of observation, express these in terms of phase, and then try to understand how this pattern looks like. What is the angle alpha, if there is an angle alpha? Is it universal or not? And so on for these questions. The Cherenkov condition here is again omega over k is v naught cos theta. And as I explained earlier, R and T are going to be expressed in terms of phase. And we get, instead of the earlier expressions, we get some other expressions. Mathematics that I have done here is absolutely high school mathematics. There is nothing complicated at all. And these expressions are valid not only for subsonic or supersonic cases, for everything. It's a very pretty expressions as far as I am concerned. I don't know if they look pretty to you. There is this phase, which is supposed to be constant, stationary phase condition. D is that length scale. V0 by CS is always there in that ratio, so very nice. Theta is the angle of emission. And alpha, or 2 alpha more precisely, will be the angle, if it is there at all, which will contain all the emitted waves together, so sort of makes a marked line. For a fixed phase, these define lines of constant phase, and they can be expressed in parametric form. So what I need, therefore, is that I need to find cos theta, find an expression for cos theta, which allows us a range where we can talk about some sensible values of this ratio, which is this ratio of CS to V0 square. So R is ratio of CS to V0. And you see, obviously, in this expression here, we find that there are terms like this in the radical, which cannot be negative. And so if we do some careful analysis of inequalities and everything, we'll find that R square is actually supposed to be between 3/4 and 1, which means that the speed of the object for Cherenkov emission and the resonance condition to be met must be greater than CS, but less than about 1.15 times CS, or more precise, square root 4/3 CS. In this range,
if I may interrupt, you have 5 more minutes left.
Okay, thank you. This is very helpful. Very helpful. I'm just left with some pictures. First picture. Here we have, for a ratio which is allowed, 1.1, x theta versus z theta. This object is moving. This is the type of emission that we observe. These are the wet solutions. The patterns of waves are confined in this. There are similar pictures for different V0 by CS. I'm just showing a representative picture. The picture with the angle which contains all these waves, the cone condition, will be obtained by this definition. So tan alpha can be entirely expressed in terms of the ratio R square, with all these radicals to be taken care of. And the alpha is therefore, actually, these are the values of alpha which are considered. So there are two branches, the blue and the orange. So let's forget about the blue branch for the moment. The yellow, so there is this orange branch which says that the alpha can be from 0 degrees to 50.89 degrees. So it's not universal. It depends on the speed. So for different speeds, there will be a narrower or a broader Kelvin-like wake. So wakes are there indeed, and wakes are Kelvin-like wakes, except that there is a dependence on the speed of the object. Okay, so if you feel, no, I mean, this is not as beautiful as we imagined it to be. First of all, I had a discussion with Professor Chitre many years ago, and he absolutely liked it. He said, why don't you publish this thing? I said, I will one day, perhaps. When I sit down and write this, I didn't know that I'll sit down and write this for his memorial. So let me tell you that it's not so bad that we got the Kelvin-like wakes which depend on the speed of the object, because even for Kelvin wakes, in 2002, the analysis of Lord Kelvin was challenged. Actually, there are comments about it by James Lighthill much earlier, but it was actually challenged in 2002 by Reed and Milgram, that they observed narrower wakes. And so actually around 2013, Rabau and Muazzi showed that ship waves, or the Kelvin wakes, undergo a transition. And and therefore it's not. They also, get narrower if you have higher speeds, which is exactly the ion acoustic waves. So that saves our day to some extent. As I said, these studies are of great importance in naval hydrodynamics, and actually, there's a specific dependence on this wake angle, which is to the Hull Froude number. The Hull is Hull rate is L, this parameter L, which depends on the size of the ship. So, it depends on the size of the ship and many other things. So we don't have time, and I don't have the desire to get into these very complicated things, as I know that even my first year students, at least one of them is there. I want to speak to them. And there are many other younger folks which are in the audience. I know that. So suffices to say that there's a dependence on ship parameters which comes through Froude number. We understand that, and we can explain the deviation. Last thing that I want to say is that there was a very interesting observation by ion acoustic-like waves generated by electron beams emitted by the tethered satellite system reflight, and the spacecraft particle correlation experiment detected fluxes of energetic electrons and ions that were simultaneously modulated at low frequencies. These modulations have been interpreted or have been thought to be interpreted signatures of large amplitude ion acoustic waves excited in Cherenkov interactions. These have been hypotheses. They are of importance because when the space shuttle enters Earth's atmosphere, the ratio of the speed is exactly in the range that I mentioned between CS and 1.15 CS. That's the speed with which it enters. It actually creates Cherenkov emission in ion acoustic waves, which is explained here in very simple terms in a linear analysis. A more detailed analysis is possible, exists in the presence of magnetic field, and is of value to the space science people, and so we were not doing that here. So that is one of the other the connections. In the end, I would like to say that the discussion I made is a leaf from a book, Book B, which we are writing. We are trying to complete. It's in progress with Bhooshan Paradkar and Professor Chitre. Professor Chitre desired it to be completed by the end of the year 2020. The pandemic and everything else did not allow this possible, and then we lost him. I'm determined to complete it, and I have a great help from Bhooshan Paradkar, and we are going to get this done. And I just want to thank everybody, all the organizers, to give me an opportunity to present this. I apologize once again if the presentation was very far too simple and very simple mathematics, but I hope the phenomena underlying is very rich and also very beautiful. Thank you very much.
Thank you very much, Professor Jain. It was a beautiful talk, and there are a couple of questions now. One question is by Avani Sejwal, the first question, and the question is as follows: would
She's
the
from
shape
first
of
semester.
pardon me?
She is the first semester student.
Oh,
second semester, first year student. Yes.
Okay.
Yes.
Would the shape of the body, which is moving on water, affect these waves in any way?
No. You mean in case of water, right? No.
Yeah.
Well, as soon as I say no, I can correct myself. If it's a needle, and if there are capillary waves which are possible, then there are different type of waves for capillary waves. So that's possible. So, but only if the shape becomes so different that we need to consider capillary waves.
And then we have another question by Sushobhan Chattopadhyay, and the question is the following. Is the D in the ion dispersion relation of acoustic waves related to the dBi length?
Related to the
dBi length?
Yes. It's exactly the Debye line. It's a kBTE by 4 pi e square NE. Yeah, so Shobhan is also my former intern student, now doing PhD in PIFR.
Ah, I see.
All friends here.
Ah, yes, of course. All right, I don't think there are any further questions. And so let's thank Dr. Professor Jain for this very beautiful talk. Thank you very much. Okay, so maybe we should move over to the next talk, and that is by Dr. Bhooshan Paradkar. Now, Dr. Bhooshan Paradkar, he did his PhD from the University of California, San Diego. And this interesting thing about him is he's an engineer by training. Then now he's a theoretical physicist. Currently, he's with us. He's a plasma physicist, an expert in particle in cell kind of simulations. So, Bhushan, why don't you begin?
Thank you, Ameeya. Am I audible?
Absolutely.
Okay, thank you. Thank you for first of all giving me this honor. I mean, to talk in the memory of Professor Chitre. I worked closely with him since I joined CBS. We shared the fluid mechanics course together, and we worked on various problems almost on a daily basis. We used to interact. I learned so much that I mean I'll carry forward those memories all along with me. What we are going to discuss today is in fact what we worked together on a problem, and then apart from Professor Chitre, I would also for today's talk I will also like to thank Professor Vinod Krishan. Both of them actually guided me in this area. I had, as you said, I was an engineer by training and I had no clues in astrophysics. Both of them were patient with me in terms of till I pick up few things. And I hope what we discuss today will be of some interest to the audience. So what I'm going to talk about the role of ambipolar diffusion in the solar atmosphere. Just see. Okay, so let me start by first talking about what we call it as a plasma universe. So if you take the density temperature plot, where y-axis is the density and x-axis is the temperature in Kelvin, and I've plotted various plasmas that one could get in the universe. We can see that there is a considerable part of the plasma which is below about 10 eV. You can expect that the plasma that is lying on this region will be partially ionized because of the low temperature. So there you would find interstellar medium. Then there's an ionosphere, photosphere, some part of the chromosphere also of the sun that we will see. Then there's this curious state of warm dense matter, which is of interest to the laser plasma community as well. So there also you may find some partial ionization. So the point I want to make here is partially ionized plasmas are essentially ubiquitous. You can find them everywhere, and Professor Vinod Krishan was saying on the first day of the symposium that solar atmosphere, if you look at it, I'm plotting the density, temperature, and the collision frequencies of the inside the solar atmosphere, where distances are taken from the photosphere. So 0 is the photosphere. So if you look at it, this blue curve is a neutral density, and the red and the black curves are the proton density. So this is taken from the Fontella 1993 solar atmosphere model. And curiously enough, because when the temperatures are almost in the photosphere, they are almost 4,000 or 5,000 degree Kelvin, you would see that the neutral density is almost 3 to 4 times, 3 to 4 orders magnitude higher than the plasma density. So especially this region of photosphere to lower chromosphere is actually weakly ionized, and this is the region where we want to see whether something interesting can happen in this region. So what interesting can happen in such weakly ionized plasma? First thing that would appear to us is what is known as, or now known as, ambipolar diffusion in the weakly ionized plasma. So this idea of ambipolar diffusion was first proposed by Piddington, Cowling, Mestel, and Spitzer in of course in separate publications, but something around 1995, 55, 56. So another reason this paper was also close to, this topic was close to Professor Chitre was Mestel, Leon Mestel was his PhD advisor. Cowling was his, he worked with Cowling after his PhD when he joined Leeds. So he had very high regards for these people. So this idea stayed with him. So when I joined, he sort of gave me this as one of the problem one could look into. So what is this ambipolar diffusion? So as we saw that we have this plasma which may have an electron, ion, and neutral fluids, and these fluids can interact with each other through collisions. So in a weakly magnetized plasma, although neutrals should not expect any Lorentz force, but through the neutral ion collisions, they can indirectly get dragged. They can indirectly experience the magnetic fields because ions, of course, experience magnetic field, and then they can get coupled with the neutrals. Conversely, the neutrals can also drag the magnetic field with it through the again same electron neutral ion collisions. So this makes it a very curious case of this multifluid plasma, and clearly for such treatment, the standard MHD models that we use may not be adequate, and this is where the interest lies, that what would modify in the standard MHD models. So one way to estimate this ambipolar velocity is to simply balance the Lorentz force on ions with the collisional drag due to neutrals. So with that, you can estimate this ion neutral drift velocity. So this is simply Vi minus Vn. So we call it as an ambipolar velocity. So it's a drift velocity between ion fluid and a neutral fluid. Now, once you have that, you can rewrite the Ohm's law for a weakly ionized plasma. And this was discussed in detail by Professor Vinod Krishan. Where essentially what we are doing is we have actually Vi cross B, we are going to write it as Vn plus minus Vn. So you have Vi minus Vn, you substitute it here, and then you get these two extra terms. So you have this classical Spitzer conductivity, then you have an ambipolar resistivity, which basically it's, if you call it as J cross B, because you have a Vm here. So you would essentially you would have you would expect a B square dependence with this J, and then there is this current helicity. So you have now a modified form of Ohm's law in a weakly ionized plasma, and in that case, you can actually estimate what is this ambipolar against Spitzer ratio. So what we did is we estimated that ratio. So essentially, you take a typical magnetic field, you take a solar model, you have this collision frequencies as we have seen earlier, and then you can actually compute this non-dimensional ratio, which basically is telling you how much is how much important is this ambipolar diffusivity. And what we found here is actually, this for a typical magnetic field, again, we are using the same Fontella 93 model of the solar. And again, you would find that for a typical magnetic field of 100 Gauss, the ambipolar, this ratio that ambipolar diffusivity can be can be 10 times more than the classical Switzer diffusivity. So the whole idea of using a standard MHD model for a solar atmosphere needs to be looked into with a bit of a skepticism. So if it's important, and then if it's because it has got a B-square dependence, so you may expect that the dissipation of magnetic fields in the solar atmosphere can also be affected by such diffusivity. So first, what we did when we started off this is basically we looked for a mean field formulation for this with this ambipolar diffusivity. So essentially, as we do it in the mean field calculation, you write a mean quantity plus the perturbed quantity, and then you average them, and then you can typically get your alpha effects and the so alpha is the helicity, and then the dissipation. So beta is the dissipation. So this is the mean field magnetic induction for a turbulent weakly ionized plasma. So where you can see here, this curl is operating on this fluid velocity. So if you have a velocity shear, then it can produce a magnetic field, or it can from some magnetic field dB/dt can be produced. So this is what we will call it as a alpha omega effect, as we will see. Then there is this alpha effect, which is basically a helicity driven. So helicity, if you see here, is defined as is basically V dot curl of V. So it's how it will tell you how helical your these correlations are. And curiously, what happens if you work with an ambipolar diffusion, because now your V is actually in terms of there is a J cross B also there. So you have, apart from what you typically have as a kinetic helicity, you also have a Hall helicity in it, which is given by this Jn prime cross Vn. So this quantity. And then there is an ambipolar. So not only you have a standard kinetic helicity, now you have a Hall and ambipolar helicity also present, and which are dependent upon magnetic field. So equations are already becoming nonlinear. So the typical dynamo equations, alpha omega dynamo equations, which are linear equations, are now, because of this dependencies, are becoming nonlinear. Similarly, you are getting you're also getting this beta, which is a standard turbulent dissipation, and the corresponding Hall and ambipolar dissipations. And then there is this B square term that we saw. So this is the standard ambipolar dissipation term. So so you have now a nonlinear sort of a induction equation. And the next thing was to check is, now we know that this is sort of an alpha omega dynamo. So let us see what happens with what happens to an alpha omega dynamo with ambipolar diffusion. So we have a standard form for the large scale magnetic field. This part is a toroidal, and then this vector potential curl will give you a poloidal part. The choice of the magnetic the coordinate system was, you're taking this theta phi z. So phi component, I'm putting it as a y component. So if you see here, so this so Vn here is basically would be the rotation speed that of the fluid that we will be locally looking into. And then with these large scale magnetic field and the velocity, then we can actually go back to this equation and write the toroidal and the poloidal components. So this is what we have done here, and this is how our alpha omega dynamo equations come. So you have a toroidal magnetic field, which will use the velocity shear, and basically this toroidal magnetic field will be produced because taking the poloidal field and a velocity shear. So that is my omega. And similarly, the poloidal magnetic field will come from taking the helicity and the toroidal. So these toroidal to poloidal, poloidal to toroidal kind of a conversion will happen, and you can have a sustained magnetic field, which is basically important for dynamo. And if you look at it in the solar atmosphere, you have already this radial shear. So this is helioseismically measured rotation profiles, and you have this radial shear. So you have this d omega dr, which essentially will give me dv dz in my coordinate system. So I already have this. So I have omega term here, and then we are saying that you can produce this alpha terms. So you have an alpha omega dynamo already operational in the solar atmosphere as well because of this because of the presence of shear. And this is a nonlinear dynamo, unlike the standard dynamos that we look into. So with these, we actually solve this numerically. These dynamo equations we solved numerically, and what we found is this plot actually is telling me I'm basically giving you the solutions of those equations, numerical solutions, where I start with a seed magnetic field, very small magnetic field, but producing this, giving this omega and alpha as the constant input. And this red curve is when I don't have an ambipolar diffusion. So magnetic field keeps on increasing and it blows up beyond a point. But when I have an ambipolar diffusion, what happens is, because it depends upon B square, as my magnetic field increases, my dissipation also increases. And that actually clamps down, and it actually leads to a saturation of magnetic field, as you can see on this, these blue lines. So magnetic field automatically gets basically gets saturated with the ambipolar diffusion because of as the dissipation depends upon B square. Something similar happens in the poloidal component as well. So this is toroidal, this is poloidal. So because as they are coupled, as the toroidal gets coupled, gets saturated, obviously poloidal will also get saturated. And even the Hall helicity, that because typical kinetic helicity has just one single sign, but in Hall helicity, because it will depend upon magnetic field, it can have a positive and negative sign as well. So in one case, I can build the magnetic field, and other case, I can suppress the magnetic field as well. So this is what qualitatively how this ambipolar dynamo can be different from a standard alpha omega dynamo. It would be interesting to point that Stix actually proposed this alpha omega dynamo, and he introduced this alpha quenching function, where this is the alpha quenching function which was proposed by Stix, and actually it all says that when my magnetic field, this is an error function, so when my magnetic field goes beyond this some critical value, actually I'll quench the alpha. But what is interesting with the ambipolar dynamo, I don't have to do something like that by hand. I have a reasonably physical mechanism which actually tells me that if my magnetic fields are increasing, my dissipation will increase because of this ambipolar diffusion, and automatically my things will get I will have the saturation of the magnetic fields. So this is what this is the important point that we got. Then you can actually generate exactly similar butterfly-like diagram that we get in a standard dynamo with the ambipolar dynamo. So this is what the butterfly diagram that we saw at least on yesterday afternoon session. So, but this is with ambipolar dynamo. So just an alpha omega term, and this is the radial dependence. So you have there exists a serious possibility of having a surface dynamo with ambipolar diffusion. And I just want to compare the other dynamos that we have. So for example, there is what is called as a flux transport dynamo that we have. And in this dynamo, what we do is you have a poloidal free fields that are produced by this Babcock and Leighton process. It gets transported by what is known as a meridional circulation. So this large scale circulation in the turbulent convection zone, it transports this poloidal field, comes here, and then as we saw in the few slides, there is also a shear, rotational shear at the base of the surface, this convection zone. So that will be an alpha effect here. So we will produce a toroidal field. So poloidal to toroidal will happen here. And when the fields go beyond some critical value, which again is dependent by the magnetic buoyancy, you will basically, you will say that these flux tubes will rise and reach the surface. So this is a dominant dynamo model that we have, but this operates on the bulk of the convection zone, whereas ambipolar dynamo will operate mainly at the surface. As I said, magnetic buoyancy will saturate the magnetic field here, whereas here it will be by ambipolar diffusion. As we see that this dynamo is critically dependent upon meridional circulation, whereas the advantage of ambipolar dynamo is you don't need any meridional circulation, because there is as Shravan talked in his talk, that there is considerable confusion about whether we have what is exactly the meridional circulation.
Bhushan,
and as we said,
excuse me, Bhushan, You have about 5 minutes left.
Yeah, sure. So I will have a, so you will have a omega effect also at the, so this is ambipolar dynamo can be taken seriously, especially if you are considering the surface dynamo. I'll quickly go into the other problem that we worked. This is the MSc thesis of our student Neha Srivastava, and we have submitted it to now POP. So we looked into the magnetic reconnection in a partially ionized plasma. So I'll quickly go through it. So magnetic reconnection is when you have a sheared magnetic field because of the magnetic diffusivity, plasma diffusivity. It's like a boundary layer problem. The magnetic field undergoes the topological changes. So the field lines get rearranged, and it's found in the solar atmosphere, in around Earth, various places. The main point I want to make here is there are two important models for to explain magnetic reconnection. One is the Sweet-Parker model, which assumes wider sheath and plasma coming in, and then there is a outflow coming out here. It goes as what is known as Langquist number, which is like a Reynolds number with V replaced by VA and Alphen velocity, and this is my magnetic diffusivity. And for fast reconnection, there was this paycheck model, which is actually assumes that the sheath is very small, and then you produce a the flows outside it, and it curiously it goes into as a log of S instead of square root of S. So this can give you a fast, because S is very large number, it can give you a fast reconnection. Unfortunately, in the numerical simulations, typically it's the Sweet-Parker that was found. Paycheck model could never be reproduced in numerical simulation, especially with a constant diffusivity. On top of it, there is this new tearing mode instability that was introduced later by Rosenbluth, Firth and Colleen, where you could actually start making these plasmoids, small plasmoids, and then when the sheath is very small, you could produce that. So this is so paycheck was never produced. But then Batty, Forbes, and Priest showed actually that if you have a non-uniform diffusivity, which is peaking near the magnetic null, you can actually produce paycheck-like diffusion, as we have seen here, a very short region. And if you have a uniform diffusivity, you have this plasmoid formation. And the reason for that is if you have a non-linear the slippage velocity of the magnetic field depends upon eta, diffusivity. If diffusivity is higher, near null region, you have a faster diffusion. So the field line curvature will be formed, which will be favorable for reconnection here. Whereas in other cases, as the sheet becomes thinner, you can produce a secondary reconnection at these points and plasmoids will be formed. But the reason for nonlinear diffusivity was given to anomalous diffusivity, which was given to essentially was linked to the current-driven ion acoustic turbulence. But curiously, with ambipolar diffusion, we find that such suppression of plasmoid instability happens. So we have this MHD simulations that we performed without ambipolar diffusion and with ambipolar diffusion, and we could see that in this case, when I don't have an ambipolar diffusion, I have a plasmoid instability, whereas in this case, I do not have any such thing. So I can produce a paycheck-like fast reconnection in the partially ionized plasma. And why is that happening? So to look into that, if you look into the magnetic fields inside the current sheath, you see that they are already centrally peaked. Peaked is 0 is my near magnetic null region, X is equal to 0. So it's centrally peaked. And then my diffusivity depends upon B square. So this is also centrally peaked. So my the slippage velocity is higher near the null. So effectively diffusivity is centrally peaked. And then I can have actually the null formation or the favorable reconnection region only near the null. So it can actually, ambipolar diffusivity can give you a simpler mechanism to produce central peak diffusivity, unlike the micro instabilities that were proposed earlier, and it can give you a paycheck-like reconnection. So this is also another thing that I'll quickly talk about, that if I have a ambipolar diffusivity, because if you see again here that the slippage velocity depends upon this. So if I have a magnetic field profile as tan hyperbolic, I can actually produce a thin current sheath. So As I increase the ambipolar diffusivity coefficient, you can see that thin current sheets are formed. Without ambipolar, there is no magnetic reconnection. So you can actually form a thin current sheets without any driving velocity or as they call it, as a driven reconnection. I'm sorry. So overall, it can also provide an ideal site for reconnection. So I'll just put my final conclusions that reconnection offers an interesting aspect to look into the spatially temporally ambipolar diffusion offers an interesting aspect to look into the spatially and temporally varying magnetic diffusivity. We looked into the possibility of driving a surface dynamo, and again, another possibility that we looked into is the magnetic reconnection in a partially ionized plasma. So it can produce a qualitatively different result, and it's worth looking into. So with that, I'll stop my presentation.
Thank you, Bhushan. It was a brilliant talk. Well done.
Thank you.
So there are a few questions. The first question is by Devesh. He says, could you please give an estimate of the mean free path in this weakly ionized plasma compared to the fully ionized plasma?
So you can look into of course, it depends upon the density, and I don't have the exact number in front of me.
Fine. The second question, again by him. It's by classical diffusivity, do you mean Spitzer diffusivity?
Yes, that's right. Yeah, it's a Spitzer diffusivity.
Okay. Then they have a question from Prithvitosh. Physically, what is meant by quenching the alpha?
Yeah, so you have this helicity which is driving the helical turbulence, which is driving this basically, essentially what this alpha term is doing is winding up magnetic fields. So you have a straight magnetic field, you have this helical turbulence that will, it's like you're winding it up. Somehow if that winding is stopped, then again you cannot, that conversion from toroidal to poloidal will not happen. And that is what people were putting it by hand, whereas we show that you don't have to do that. You can counter it by increasing dissipation.
Sorry. Then we have a question from Amit Seta. What are observational signatures of a bipolar dynamo?
No, we are not talking about bipolar dynamo. I mean, not
bipolar. Sorry, I read it wrong. It's ambipolar. I'm sorry for that.
Yeah, there have been
ambipolar dynamo.
Yeah, ambipolar. There are the surface dynamos are being discussed. I think for example, Brandenburg has also looked into surface dynamos. I don't know whether any other ambipolar dynamos have been explored, because it would happen in that narrow region of a few hundred kilometers, etc. But what we observe in the magnetic fields is also in that near photosphere. So the other ideas that we are proposing also, there is no conclusive evidence for that as well, as in the flux transport dynamo. These flux tubes that happen at the base of the convection zone have to be transported all the way 0.3 solar radius. There is no full-scale simulation for that as well, so we don't know actually which dynamo.
Okay, so Bhushan, should we have one more question or should we call it a day? We still have time. We still have time, so we still have a couple of minutes. Maybe I can take one more question.
Okay.
Sanskriti? Now, there is a question, I don't know who has asked this question, but how does Touling's anti-dynamo theorem apply to ambipolar system?
Oh, we are not violating any anti-dynamo here. This is essentially the same as there's no violation of that. This is essentially the same alpha omega dynamo. We are just making it nonlinear with the nonlinear diffusion and alpha terms.
All right. So if there are no further questions, then let's thank again Bhushan for this very beautiful talk.
Thank you, Ameeya.
Thank you so much.
Thank you.
Okay. So now we go to the next talk, the last talk of this session, and it's by Aklant Bhowmick. It's again nice to see him. I mean, a student who, I mean, he's from our third batch. He finished his PhD from Carnegie Mellon University in 2019, and at present he is a postdoctoral research fellow at the University of Florida at Gainesville, USA. So, Aklant, welcome back, and why don't you quickly begin?
Absolutely.
Good to see you.
Can you guys all hear me?
Yes, loud and clear.
Can you see the slides?
Yes.
Awesome. Okay, so thank you so much for the kind introduction, Ameeya. And it feels really great to be back in CBS, although it's via Zoom after a very long time. It's been 7 years, and hopefully once this pandemic is over, I'll also be able to visit in person. And so I'll move forward with my talk, and my talk is going to be about cosmological simulations of galaxy formation. A very apt topic given the broader theme of this conference, because when you talk about galaxy formation, it is essentially fluid mechanics solved at the largest possible scales that you can think of, which is the entire universe. So the background panel that you see here is essentially a movie of a very recent simulation that's been run. And you can see the formation of cosmic structures at the largest possible scales. And this is just to say that these simulations come with a huge amount of computational as well as human effort. But at the end of the day, it's all worth it, not just because of the extraordinary amount of science that comes out of it, but also for the simple privilege of being able to take a gallery seat view and witnessing the evolution of the universe as it's happening. And before I proceed further, I'd like to take a brief moment and dedicate my talk to late Professor Chitre. He's truly been a huge mentor and played a huge role towards me starting my career as an astrophysicist. So my very first publication was with him, and he will continue to be a source of inspiration for me in the years to come as well. So back to galaxy formation. So no conversation about galaxy formation can happen without involving cosmology, because as I mentioned, galaxy formation occurs at the largest possible scales where cosmological implications simply cannot be ignored. So everything that I'll talk about today about galaxy formation basically rests under this framework of the standard cosmological model that we talk about, which is the lambda CDM universe in a hot Big Bang model. So when I say lambda CDM, you have lambda, which is dark energy, which occupies about 70% of the present day universe. Then you have CDM, cold dark matter, 24%. And then the remaining tiny 4% is basically your everyday matter, which cosmologists collectively refer to as baryons. And then you have a small amount of radiation as well. Here you see the timeline of the universe, which is probably something that you've seen in previous talks as well. And this is based on the hot Big Bang model, where the universe starts with the Big Bang singularity, followed by a brief period of exponential expansion called inflation. Here is the cosmic microwave background, where the universe becomes neutral for the very first time. And then you have a short, relatively uninteresting period called dark ages, where nothing is really happening until the formation of the very first stars, which then paves the way for the formation of the first galaxies. And then they evolve all the way to the present day universe. And then with respect to the present day universe, it's basically marked by an astonishing diversity of galaxy population that you see here, which is kind of summarized in this Hubble tuning fork diagram, which is used very typically to characterize galaxies in terms of their shapes. So in the base of the tuning fork, you can see some elliptical galaxies. And then as we gradually move towards the front end of the tuning fork, you can see more and more spiral galaxies. And then you also have some irregular galaxies, which don't quite fit into this classification. But essentially, the broader goal of galaxy formation is to try and explain this diversity of galaxy populations that we see from fundamental physics principles. With respect to cosmological simulations, the specific task that we assign to them is to essentially try and bridge the gap between the two pictures of the universe that we have at completely extreme instance of time. So on one hand, you have the picture of the infant universe about only 400,000 years old, where we have the map of the cosmic microwave background, essentially a temperature map, and these fluctuations that you see in the temperature, it's a manifestation of the fluctuations in the very initial density field of the very early universe. And the task is to try and see how these tiny fluctuations grow and evolve to give this rich structure that we see in the present day universe, which we see here in the map of galaxies from the Sloan Digital Sky Survey, where each dot represents a single galaxy. And overall, there might be about 500,000 to at least 1 million galaxies in this map. And all of these galaxies, they basically collectively form this web-like structure that we refer to as the cosmic web or the large-scale structure. And this task is essentially an extremely, extremely complex problem, largely because the range of physical processes that we now know to impact galaxy formation physics is they span a huge range of dynamic scales. So here you see some of these physical processes spanning over more than 12 orders of magnitude, starting from the smallest microparsec to milliparsec scales, where you have supermassive black holes accreting gas. Then you have star formation in giant molecular clouds in roughly parsec level scales. And then you have formation of individual galaxies between, say, 1 to 20 to 30 kiloparsecs. And then you have formation of galaxy clusters at megaparsec scales, all the way to the largest gigaparsec scales, where you have the formation of the large scale structure. So now, given all of this physics, the task is to figure out how to encapsulate all of these different varieties of physics onto a numerical model so as to produce a simulated universe. Now, fortunately, there's one property of the universe which helps us to make this task relatively simple, and that is essentially the fact that the universe is homogeneous at the largest possible scales, and this is part of the cosmological principle. And any inhomogeneities that exist only at relatively much smaller scales, maybe a few megaparsecs and less than that. So we exploit that within our numerical algorithm to kind of decouple the evolution of the large-scale homogeneous background, which requires a full general relativistic treatment. And then after that, you can solve for the small-scale inhomogeneities, which can then be solved using the Newtonian approximation, which makes our life considerably simpler numerically. So starting with the large-scale homogeneous universe, the evolution of that is basically governed by this very famous Friedmann equation, where the left-hand side is essentially the rate of expansion of the universe, and the right-hand side is the contribution coming from different components to the expansion of the universe. So you have radiation component over here, matter component. Now, in principle, you could also have a curvature component, but it so turns out that at the largest scales, the universe is flat. And then, so this component is actually 0. And then finally, you have the dark energy component, which is modeled as a cosmological constant. And it is indeed this cosmological constant, which is responsible for the accelerated expansion of the universe at the present day. So once we have this expanding universe encoded within our numerical model, then we can solve for this evolution of small scale inhomogeneities. And this is essentially where the fluid dynamics aspect of the problem comes into place. So you have dark matter, which is modeled as a collisionless fluid. So the evolution of that is governed by the collisionless Boltzmann equation evolving under its own gravity, which is encapsulated here as the Poisson equation. And then you have our ordinary baryonic matter, which is modeled as a inviscid ideal fluid. So you have the Euler's equation supplemented by the ideal gas equation of state. Given all of this physics, if you want to actually form stars and galaxies in the simulation, we also need to include some astrophysics of galaxy formation. And there's a wide array of astrophysical processes that are typically modeled in cosmological simulations. Here I'm just quoting some of the most crucial processes that must be included if you want to actually form galaxies in a reasonable fashion. So you have cooling of gas, and then formation of stars, enrichment of the gas with metals, and the formation of supermassive black holes. So once we have all of this, then we basically end up with this computational model with the simulation box over here. And then you start off with the initial conditions where you distribute matter, which is almost uniform, but they have tiny, tiny fluctuations. And then we can see how these fluctuations get amplified under the action of gravity to form these large-scale structures under which these galaxies form. And you can see these large-scale web-like structure very well qualitatively represents this structure of galaxies that you see in the SDSS survey. And then all of this is typically done in some of the most powerful supercomputing facilities in the world, largely because it's of the computational scale of the problem. So you have sometimes millions to billions, and for a few simulations, even close to 1 trillion computational elements. So it's a really, really challenging problem numerically. Lots of groups today spread across different parts of the world are pursuing this. And so this is just a collage of different kinds of simulations that have been run. And all of this data is made publicly available. So students who are interested in this can go and access data and do lots of science, and at the same time get lots of pretty images, which is also always nice. So these cosmological simulations have been pursued by various groups over about 2 to 3 decades now, but it's only been in the last 5 to 6 years that these simulations have actually started producing galaxies that resemble observational galaxies. And here is just an example of a movie from a recent simulation. This is a simulation that I use very regularly in my everyday work. That is the illustrious TNG simulation. So here's basically the gas involved in the formation of the disk galaxy, and here's the formation of star. Here's a stellar map in the inset panel over here, and you can see how these spiral structures are forming. So, and in this diagram, you can see the larger population of these galaxies that are formed in the illustrious TNG box. So you have a set of simulated spirals over here and simulated ellipticals. And you can even visually see that these galaxies do represent the observed galaxies that we saw in the Hubble tuning fork diagram very early on in the slide. If you want to make more quantitative comparisons, you can see plots here, which represent galaxy abundances. And then plots here represent the spatial distribution of the galaxies in the form of the galaxy clustering. We don't need to go into too much detail in this slide. This is largely also for me to shamelessly advertise some of my work that I did as a graduate student. But the essential point is that when you look at, even when you look at quantitative statistics, our cosmological simulations have really started to produce galaxy properties consistent with observations. Now, given all of this success of cosmological simulations that we see, the next natural question that emerges is that, do we now have can we claim from this success that we have a complete understanding of galaxy formation and the field is all said and done and there's nothing left to do? And the answer to that is a resounding no. In fact, we are far from it. And to try and explain that, I want to take you back to one of the very first slides that I showed, where you have the various physical processes again spread across this huge dynamic range of spatial scales. And the essential point is that, like any numerical model, our simulations have a resolution limit. And for these current state-of-the-art simulations, this resolution limit kind of hovers around this kiloparsec scales. So any process that is occurring at scale smaller than that simply cannot be modeled from first principles. So in this case, you can see star formation in giant molecular clouds or accretion of gas onto supermassive black holes. They simply cannot be modeled from first principles. So what is typically done to deal with that is that we construct these sub-resolution models to model these processes. So here's a very incomplete list of a few processes that absolutely requires sub-resolution models. So we have the modeling of the complex interstellar medium, which is very, very poorly resolved in these cosmological simulations. And then you have formation of stars, formation of black holes. And then you also have feedback processes from stars and black holes through which they inject energy into their surrounding gas and regulate star formation in the process. Now, with all these sub-resolution models, they come with various, a rather large parameter space of these free parameters. And these parameters are extremely uncertain and cannot be determined from first principles in a very trivial way. So what is typically done is these are often calibrated against a very limited set of observations, particularly from the low redshift local universe. So all this is fine, but now we have a now we have different groups pursuing different simulations. So you have, for example, the illustrious TNG group doing their own simulations, and then the Eagle simulations and the OWL simulations. And they all use different kinds of subgrid models. And within, even if they use the same subgrid model, they may use different set of parameters. And all of these groups who are publishing papers, they're all finding very good agreement with observations. So the question is, which model is correct and how do you break the degeneracy? So, and this is basically where most of the current efforts are directed, which is that as these simulations are going to inevitably reach higher and higher resolutions, we really need to refine these sub-resolution models to include more physics in terms of more explicit models. So here's just an example I'm showing you from a very recent work, which did that with the modeling of the interstellar medium. So here's a galaxy. It's the same galaxy in both these panels, same resolution, much higher resolution than what is typical of current cosmological simulations. And in the left-hand side, you have an rather old interstellar medium model, which was also used in the illustrious TNG simulation, for instance. And then this is the same galaxy with the new interstellar medium model, where you have more explicit modeling of, say, feedback from stars and star formation, et cetera, et cetera. And you can clearly see even visually that the new model produces features in the gas density profile, which simply cannot be resolved in the old ISM model, even if both simulations are in the same resolution. So this is just an example of, for saying that these simulations, with these newer models, we can really do newer science, which simply cannot be possible with current or older models. So my current work is basically in the same spirit, where I'm developing these subgrid physics models for supermassive black hole formation to be applied for the next generation cosmological simulations. So the remainder of this talk, the few minutes that are left, I'll use to very briefly summarize the work on this that I'm doing as a postdoc in University of Florida. So just to give you a little bit of a background, we know that supermassive black holes are key drivers of galaxy formation, and almost every galaxy has a supermassive black hole. And this is evidenced from this very famous M sigma relation, where on the y-axis you have the black hole mass, on the x-axis you have the velocity dispersion of stars in the stellar bulge. And you see a very tight correlation between these two variables. And if you think about it,
you have a few minutes left.
Okay, thank you. I'll be done. Yeah.
Right.
If you think about it, this is rather surprising because the black hole mass is a very tiny component of the overall galaxy mass. So the question is, how does the galaxy, quote unquote, know, so to speak, about the black hole? So the broad goal of my current research is essentially to figure out how and when do these supermassive black holes form in galaxies, and what were the masses of these very first seeds. And this is also the broader science goal, one of the science goals of these upcoming set of observatories, JWST, LINX, and LISA. So from a theoretical perspective, there's a wide range of processes. Well, there's various theoretical channels that have been proposed. So here's just two relatively popular ones. So you can have on one hand remnants of the very first generation of stars, population 3 stars that can form the first seeds. And these seeds are typically going to be of the mass of 10 to 100 solar masses. And then on the other hand, you can also have formation of black holes forming when gas can directly collapse. A huge amount of gas can directly collapse onto the central potential of the halo. And these can form relatively massive seeds, 10 to the power 4 to 10 to the power 5. So, and the point with regards to cosmological simulations is that current simulations simply are not able to resolve these processes, because the typical mass of a single gas resolution element is about 10 to the power 6. And you can already see that these black hole seeds are substantially smaller than this resolution limit of the simulation. So here's just a plot that I'm going to use to summarize what I did in one of my very recent papers, which is going to come out very soon. And so so I basically simulated a small patch of the universe at increasingly higher and higher resolutions. So you can see the evolution of that patch from top to bottom panel, from redshift of 20 to redshift of 8. As we move from left to right panel, I'm representing the same region at increasingly higher resolutions. And the idea is that as we move to higher and higher resolutions, you can basically solve for the formation of black holes. You can model the formation of black holes at increasingly earlier times, and you can model increasingly smaller black holes, as you can see with these green circles. For instance, at redshift of 20, you can see the formation of very tiny black holes over here, which is completely absent in the lower resolution version of the same simulation. So the idea now is to use these super high resolution simulations to really try to develop these black hole seeding prescriptions, to try and incorporate more physically motivated black hole seeding prescriptions for the upcoming set of cosmological simulations. And with that, I'm gonna leave you with my summary, saying that cosmological simulations they try to attempt to model the physics of galaxy formation by solving for the fluid mechanics problem at the largest possible scales. And these simulations are now able to reproduce many of these observed properties of galaxies. That being said, which is undoubtedly a huge success, because even 5 to 6 years ago, people were nowhere close to achieving that. And then that being said, there's still a long way to go, because there's uncertainties in the sub-resolution models, and it's a major hindrance towards developing an actual understanding of galaxy formation. So current efforts are basically directed towards these sub-resolution models with more explicit modeling of the physics, so that we can rely less and less on calibration against observations and make our simulations more and more predictive. And with that, thank you so much for inviting me to this talk, and I'll be happy to answer any questions that you may have.
Okay. Thank you, Aklant. It was a very nice talk, very well structured. And now we have a couple of questions for you.
Yeah,
the
absolutely.
first question is by Avni Sejwal. And the question is as follows. What are applications of the understanding of galaxy formation for us here on Earth?
Yeah, that's a good question. I mean, we're basically trying to understand fundamental physics. So, I mean, you could ask the same question for literally every field in astrophysics, and this is an astrophysics conference. So, yeah, I mean, you're trying to understand how fluid dynamics works at a wide range of scales. You're trying to understand, so galaxy formation, understanding galaxy formation, for instance, is extremely crucial to understanding cosmology. And people on Earth, a lot of people on Earth are interested in understanding cosmology. So yes, and then, for example, with galaxy formation, there's wide range of, you need to understand fluid mechanics at a wide range of densities. And some of these densities are also relevant towards various processes that are here on Earth. For example, extreme densities in the universe where these galaxy formation works, that can also be emulated on Earth. For example, modeling of, say, nuclear fusion, and then rocket propulsion, et cetera, et cetera. So all of these are very translatable problems, even if you solve for, even if you're looking at astrophysical scales, they can also be translated into an understanding in our everyday terrestrial scales, yes.
All right, you have get another question. It's from Debesh. I'm just curious if we could have a weakly interaction instead of collisionless Boltzmann equation for the dark matter, so that the system could evolve into a Maxwellian type.
So I mean, people have looked at alternative dark matter models, but essentially, I mean, even if you include a weak interaction, the cross section for that interaction is going to be so small that you can still, the collisionless approximation is going to hold pretty well. So I don't think it would make a significant difference to the results. Now, there are alternative dark matter models which would make, like warm dark matter models or fuzzy dark matter models, which would start to make a significant amount of difference to the galaxy populations, particularly the low mass galaxies. So yeah.
Okay, I think there don't seem to be any further questions. Aklant, good job. Nice to see you after a long time, and you're doing a very good job.
Good to see you all too.
So,
Ameeya,
well done.
there is one more question.
Okay, let's have it, because anyway, the next session begins at 1645. We have overshot a little bit, but that's okay. We can take another question. Okay, the question is the following. How much time does it take to finish a simulation? Is it possible to work the other way around, moving towards the KPC scale? It's from Hari Tejas S. Iyer.
Okay. So that is a very good question, because it really depends on the scale at which you're performing these simulations. So I'll start with like some of the most popular cosmological simulations, the standard typically 100 megaparsec box sizes where you're trying to resolve KPC scales. So if you want to go from, say, a redshift of 100, which is typically where cosmological simulations start, well after the matter radiation equality, if you want to go all the way to the local universe, then it could take maybe somewhere to a couple of months, to 3 months, 4 months, maybe 6 months. And then as another example, the TNG50 simulation, if you know what, so it's the illustrious TNG suite, the highest resolution version. It's relatively small volume, but it's very high resolution compared to the 100 megaparsec scale simulations. That ran for a significantly longer time than even what the group members had anticipated at that time. So it ran for about 1 to 1.5 years, all the way to redshift 0. So yeah, they published the other versions of the other realizations of the illustrious TNG model at least a year before the last highest resolution version was published. So it is interesting. Now, the simulations that I work with, which are so-called zoom simulations, where you're trying to simulate a small patch of the universe, but in a cosmological context. So you have a larger region, which is simulated at low resolution, and you have your region of interest, which is simulated at a very high resolution. That usually you can go at least like 1,000 times higher resolution than your typical cosmological boxes, but still simulate it within a matter of like a few weeks. So that's why I'm using these. People use these zoom simulations, so to speak, to develop models. But once you have these models developed, they can apply to these cosmological runs, which can then take years, months and years to complete. But the good thing is that while these simulations run, you can still publish papers. So it's not like you have to wait all the way for the simulation to reach the local universe and then you start publishing papers. Otherwise, my postdoc will finish before I can publish a single paper. So as these simulations make progress, you have various epochs through which the simulation goes through. And you can publish papers on what the universe is telling you about those epochs.
Excellent. So I think we don't have any further questions. There are no further questions, I suppose. So thank you very much, Aklant. It was a very nice talk.
Yes, thank you. Good to see you all.
Yeah. So the session is now over. So the next session begins at 1645. So we have about 12 minutes of break. Bhushan?
Yes, Ameeya.
Yes. So the session is over. So when shall we meet?